So let's look at the chemistry of wetting agents. Here we have a diagram of the typical classical APE-based material with a hydrophobic end and a hydrophilic end. Newer generations referred to as Gemini or split hydrophobes. It's got a double tail, hydrophobic tail, and a single hydrophilic head. Here's a diagram of Petchem's technology. We refer to it as the three-master, as a reference of the triple-masted schooner technology that we can use to replicate what this molecule is. It has three hydrophobic heads and a single it has three hydrophilic heads and one hydrophobic tail. Now, just keep that picture in mind when we talk about the function of these materials and how they operate. Non-ionic wetting agent, typically used in paints and colorants. Because of the number of and the variety of pigment affinity groups that's on the various hydrophobic ends, it can be used to stabilize and help wetting of a multiple variety of different types of pigments. The dense packing of the hydrophilic groups offers an increase in stability, especially in waterborne systems. And the proximity and the number of multiple hydration sites resists coiling and flocculation. And we'll see an example of that. So, and it's resistant to the alkyl chain coiling up because of the proximity of these three alkyl chains that are packed on that molecule. And it's APE-free. So schematically here, we have a diagram of what the EPA wetting agent does during film formation. On the left-hand side, we have a stabilized pigment particle with its electrostatic stabilization mechanism. And our wetting agent resides primarily in the water phase. And these blue dots represent water molecules. It's a hydrated hydrophilic polymer chain tail. So as the paint dries and the water leaves the system, now that hydrophilic tail is dehydrated. And so because there's no hydration to make it soluble in the water, what it does is it coils up. So the size of the molecule goes from this to this. And so as the film dries and everything is compressed, okay, because we're removing the volatile, now we have a volume reduction in the system. As these pigment particles now come close together, these coiled up snail-like dehydrated APE-based wetting agents, the possibility occurs that they are no longer helping the stabilization mechanism. So as the ionic strength of the system increases, okay, remember this is electrostatic stabilization around each side of these pigment particles. When enough water leaves, the ionic strength of the system now goes high and the stabilization mechanism collapses. And it may be that these coiled up molecules are no longer large enough to keep those two pigment particles from making physical contact and flocculating. So this is when during the drying stage, we do our color change rub-up test and we deflocculate if there's any flocculation, and the change in color indicates that we have created the situation where our film is flocculated and we deflocculated it during the test. Now let's look at what the A202 does. Here's the diagram of the triple master. You can see it's a different shaped molecule. Those three hydrophilic tails are packed close together. And the blue dots again represent the water hydration. When it leaves, when it dries, the water evaporates. These polymer chains are very resistant to coiling because they're too close to their neighbors. And so as these pigment particles come close together, the physical spacing that these wetting agent, the A202, provides is greater than the coiled up APE type wetting agents, providing just a further molecular spacing, greater molecular spacing between the particles to help the preventing the flocculation of these two particles. And all these claims are all fine, but the proof is in the results. And so here we have a paint. The same white to color phthalo blue ratio comparing APE versus the A202. And the contribution and the improvement of the A202 is significant. You can see it right there. That's the result. This is the same paint formulation using APE on the left-hand side and just the replacement of the APE with the same amount of the A202. And then drawn down and rub up. So where can you use this DA202? Well, in the paint and coating systems, everywhere that you use typically used APEs. In interior architectural coatings, exterior architectural coatings, in slurries, wood coatings, and in construction coatings. Any place that APEs were used, you can just plug in DA202. The benefit of the DA202 has greater resistance to dehydration. So it slows down the drying just enough, okay, to give you then this additional molecular spacing benefit. And so let's look at what its improvement is. We're going to look at wetting efficiency. We're going to look at the amount of foam in various PVC paints. We're going to look at the comparison of APE versus 202 in foam generation for application, this freeze-thaw stability, contrast ratios, resistance to color flocculation. We're going to look at and water resistance, washability, blistering, and scrub resistance testing, comparing APE with 202. Remember, I did mention that the DA202 is more resistant to loss of water for dehydration, and then also more resistant to rehydration, again, when it's introduced to water after the film is dried. This is a formulation we used, and then we selected to use all petchem additives. The DA103 is the typical methacrylic acid dispersing agent that's used in the architectural industry. The whitening agent DA202 as an alternative to the APE. We chose to use PAT-AD AF34 defoamer and PAT-AD Real 100 thickening agent, our Hure modifier. And so we mentioned that we're going to look at the mill-based efficiency. Well, if the mill-based viscosity is lower, we can add more pigment into the system. And the pigment dispersion stage is the slowest step of the paint manufacturing process. So that is the most cost-intensive step of the paint manufacturing. So anytime we can reduce the viscosity of the system, will increase the productivity of your manufacturing, especially if you optimize your mill-based viscosity for your milling equipment. So as an example, in the 15% PVC paint, comparing the gray bar and the blue bar, we are at least equivalent, if not marginally lower in viscosity, comparing the APE to DA202. So pretty much equivalent, but marginally better. Foam entrapment. This is where we take the finished paint and we shake it, stir it up, and then we measure the density of that. And you can see that if we take these paints and plot them, the comparison of gray versus blue, the blue is at least equal, but marginally better in all cases of PVC, from low, medium to high. Application. This one's pretty obvious. You can see that the DA202 is much better than the APE in roller application. You can see the water, very, very small blisters, bubbles, air bubbles from air entrapment in the APE compared to the DA202, which exhibits no little bubbles. In the low PVC paint, again, the medium PVC paint, and here's the high PVC paint. Freeze-thaw stability. This is where we freeze the paint and we thaw it out, freeze it, thaw it out, freeze it, thaw it out. And on the 5th day on the test, and we plot the measured viscosities, you can see that the red line, which is DA202, and the blue line, which is APE, are pretty equivalent, almost the same. The slope on the 202 is slightly less, so measurably better, marginally. This is in the low PVC paint. pretty equivalent in the medium PVC paint, but still measurably minimal improvement. And then in the high PVC paint, again, equal or measurable slight improvement. Contrast ratio. This is where we apply the paint with the same pigment loadings over black and white charts, and then we measure the difference in opacity. And you can see that there's a slight increase, but it's measurable improvement comparing APE versus DA202. But here, this is dramatic, okay? This is not a marginal improvement. This is what your customers see when they open up their can of paint. If the customer has bought the paint, it's tinted, it's shaken, he takes it home, and it starts to rain, and he says, I can't paint now, it's raining, and then he forgets about it, and comes back after some time, the paint that he thought would look uniform looks like this, comparing the APE versus 202. Okay, on the left-hand side, we see after 24-hour storage and after 1 month of storage, there's a dramatic separation of the colors and the particulates and the particles in the APE paint, whereas in the DA202, it's much less so, or it's not visible. These are at room temperature storage conditions. At elevated temperatures, it's even exaggerated. At a higher PVC, again, showing 24 versus 30 days, 1 day versus 30 day storage. And then the improvement in color rub-up resistance. This is on a high styrene acrylic-based paint. Now we're going to look at the actual rub-up. And this is going to be done pretty shortly after application because it's dry enough that it's not fluid enough to recover from this rub-up that we apply. And the improvement, you can see that will be significant comparing between the APE and the DA202 paint. The rubbed up spot is higher intensity in color, indicating that our red or violet pigment has flocculated. And on the right-hand side, it's marginally, you can't see any difference between where you've done the rub-up. And finally, we're going to look at the water resistance. Here we compare the high PVC paint scrub test. This is where we take abrasive media with water, surfactant, and abrasive media and a brush, and we put it on this machine that draws it across. On the underside, we'll put a brass shim so that we make edges for this brush to go back and forth. And you can see that there's an improvement comparing APE versus the A202 in the number of cycles that it's resistant to exposure of the substrate. It's an indication of sensitivity to water and abrasion resistance and the presence of surfactants. Water resistance test, again, this is a high PVC paint, which is more sensitive because high PVC paint has less binder as a percentage of the total formulation. On the left-hand side, we can see the collapsed blisters from this water immersion test. This is 3 days of water immersion after the paint is dried. Blisters with APE and no blisters with the A202. Remember, I did mention about the resistance to rehydration after the film is dried. And then the washability test, comparing the blue bar, which is APE, and the A202, which is the orange bar, and equivalent performance in many, many tests, but some improvement, significant visible improvement with other tests, depending on what is used to mark the substrate. So if we go down our checklist, we can see that 202 versus APE has better wetting efficiency, better resistance to foam entrapment, better resistance during foaming to application. It's at least equal, if not marginally better, for freeze-thaw, viscosity, stability at various PVCs. It shows a measurable improvement in contrast ratio, color stability, resistance to color change on rub-up, and then the improvement in water resistance, washability, and scrub test. So in all cases, Da202 is going to be at least equivalent, if not slightly better, than the APE product. So what conclusions can we draw from this? Petchem's three-master technology, because of the triple hydrophilic groups, gives superior performance. And actually, it's very easy to test and use. You can use it as a drop-in pound-for-pound alternative to the current APE-based wetting agent that you currently have in your formula. So it's easy to test. You can take your formulation of choice. Our preference is, of course, using all Petchem additives. 103 as the dispersant, stabilization, 202 as the wetting agent, AF34 as the PDMS, mineral oil-free defoamer, and the Reol 100 as the Hura thickener. But in your formulation, you're probably not going to want to reformulate everything. So my suggestion is always just to take your existing formulation, use however you have it formulated, and just substitute Da202 for the APE that you have in there. And then run your laboratory stability test.